went over on Tuesday, a lot of that's coming back to me.
Oh, that's cool to hear. Awesome.
Yeah, I recognize it. I remember this. Decades and a half ago.
That's always satisfying when you see it starting falling into place.
You
Cool.
go through the filing cabinet and pull out that file.
Yeah. Yeah, we got through that section and finished it out on Tuesday's class. Oh, welcome back, folks. Looks like it's time to get started. So we got through at section 8.1. We're now looking into section 8.2 on law of cosines. This one is maybe a little bit longer, so if we have to come back to it after the exam, which would be a week away from today, that's what we'll do. We're not going to try to rush through any of these. But for the upcoming exam, which is going to be next Tuesday, it'll be constrained to just those four sections right there. 7.1 is about simplifying trigonometric functions, proving identities. 7.2 was about the addition formulas. 7.3 got into the half angle formulas, double angle formulas, reduction formulas. And 7.5 was an equation solving. It's four sections this time. It seems like a lot, but I know it's a 50-minute exam, so the exam length will still be the same. I can't ask every single type of question from all four sections. I'll just be taking a representative sample of likely questions. Well, any questions, folks, about the upcoming exam or any other questions otherwise? Okay, well, welcome back, everyone. We're going to be going into section 8.2. And again, if we need to push the due date, we will push that due date. So we'll just see where we end up on that section there. After we get through the third exam, then we're going to have a pretty normal week on April 22nd through 28th, sort of. Well, that's going to be the penultimate week of the whole class. So that means on the 23rd, that one will be a normal class. We're just going to finish up any loose ends, maybe section 8.2, law of cosines, maybe the next section right after. Then on the 25th, 2 weeks away from today, then we're just going to be reviewing for the final exam. We'll put all our efforts into that. And you're going to start to see a lot of additional problems just emerging down below here. I'll be posting old final exams, things like that, to help you get a feel for what a real final exam is going to look like and help you prepare. So that's what we have going on so far, folks. Any last questions before we jump back to section 8.2?
For the final exam, is it going to be all the materials we have covered or just like chapter 8?
It's going to be comprehensive, yes, from section 5.1 to wherever we end on in chapter 8, possibly section 8.3. Yep, you bet. I did want to mention, that's a good question, Hayes. One of the things I do on my final exam is sections 8.1, 8.2, they're not on exam 3. So sometimes people decide to put extra emphasis on those sections they haven't been examined on, but I'm not going to do that. I might just ask one question from each one of these sections. So I'm not going to try to emphasize one section or the other. It's going to be an even emphasis on everything that we did in the course. Any other questions, folks, so far? Okay, we'll talk a lot more about the final exam as we get closer and closer to that date. But really, it's all about exam 3 at the moment. So this exam is going to run pretty similarly, except this one will be an open calculator exam. Word of warning, though, most of the problems on here, we still have to get exact values on. The calculator will just be an extra tool, an extra assist that we can potentially double check our answers, that kind of thing, to see how plausible they are. But now with all that out of the way, here's how the law of cosines goes. Well, I have a bunch of white space here. So the reason for that is a good way to think about the law of cosines is to first review the Pythagorean's theorem. So I want to put in a right triangle. Goes about like this. It needs to have what looks like an obviously 90-degree measurement. And then you would typically label the legs of this triangle something along these lines. A, B, and C usually is the longest length, the hypotenuse. So Pythagorean's theorem says C squared is equal to A squared plus B squared. So if you have a right triangle, Pythagoras theorem says this is how you can relate all the side lengths. So we love Pythagoras theorem. We use it to define trigonometric functions. It became the Pythagorean identities, cosine squared plus sine squared equals 1. But now we have to extend beyond this because we're looking at non-right triangles. So if that's not exactly 90 degrees, Pythagoras theorem is wrong. So here's what the extension to that theorem is going to look like. I want to try to draw a triangle that doesn't look like it has 90 degrees anywhere. So how about this one? Even extend further. There we go. I don't think that would look like it has 90-degree measurement to any of those angles, to anyone's eyes. Now, once we have that, let's read through the law of cosines. The law of cosine states that the square of any side of a triangle is equal to the sum of the squares of the two other sides minus twice the product of the other two sides and the cosine of the included angle. If you're like me, that didn't make any sense. So what we have to do instead of reading through that is, let's just put down angles. You can go capital A, B, and C. By the formulas down here, you could also go alpha, beta, gamma, completely up to you. I'll go with the Greek letters, alpha, beta, gamma. We decide on alpha, that immediately on this side, we need to put the side length A. If beta goes here, then the side length B will go on the opposite side. And for gamma, put a side length C over here. So now that we have this information, let's see if we can read through this again and see if we make sense. The law of cosine states that the square of any side, so let's pick a side. There it is, of a triangle is equal to the sum of the square of the other two sides. Hey, that's what this is saying, sum of the squares of the other two sides. So here's c squared, the sum of the squares of the other two sides, minus twice the product of the two other sides. And that's what this is. Minus 2ab is minus twice the product of the two other sides. And the cosine, I guess that's why it's called law of cosines, of the included angle. What do they mean by that? Well, we started here, we squared those two sides, A and B, and gamma is the included angle. So that's why you see a gamma there. So that's what the law of cosines is all about. And as weird as it sounds, Pythagorean's theorem is the law of cosines because you can put this here, minus 2ab cosine 90 degrees. Reason this works is, here's the side, c squared. Opposite side is 90 degrees. It just so happens, cosine 90, anyone see what it would be? Exactly. So it's just a fluke that turns into 0 and it cancels out because cosine 90 degrees is cosine pi over 2, which is equal to 0. That's why you never see that if it's a right triangle. It's just a mathematical fluke that it falls out for that one angle measurement. It's all about the information you have. That's a really good question. There's no one better version. Law of sines is not necessarily better than law of cosines and vice versa. It depends on the information you're given. And I would say this is the absolute law of cosines kind of situation. You have an angle, you have the side lengths around them. That means you can find the distance d here really, really rapidly with law of cosines. This is like a really good case for it. If you're missing this side length, but maybe you have a side length somewhere here, maybe that number's provided in a different angle. Let's see here, what you would want that angle rather. You probably want to use law of sines instead. So your choice of using either law of cosines or law of sines, totally dependent on what side lengths, what angles you actually know. And because these things go together, when we do these problems, we will be using the law of sines and the law of cosines and see how they work together on these examples. So that's a good question, and we will be addressing it throughout the problems. First, let's take another look at all this. It says for triangles with angles alpha, beta, gamma, and opposite corresponding sides, A, B, and C, that's exactly how we built out this triangle. The law of cosines has 3 equations, and so did the law of sines, but it was just a triple-sided equality. Now let's take another look at this. On equation 1, you're squaring A. That means you should have cosine alpha right here. So law of cosines is all about square this side and take cosine of the opposite angle. Then you just use these things, C and B squared C squared minus 2 times B and C. So whether you're using alpha, beta, gamma, or A, B, and C, it's all about the pattern. It's less about the symbols you're really using. So seeing that pattern again, just to emphasize it, on this one, you see B squared, you must have a cosine beta. So we squared that. We have to use cosine of that angle beta. And notice that means C and A emerge here and here as well. And same idea with this one that we looked at earlier. So that's how law of cosines goes together. You take the square of one side, C squared plus A squared minus 2 times A times C times cosine of beta. That's our pattern that we're going to try to internalize. Any questions at all, folks, at dealing with the law of cosines so far? Okay, well, this is all about just stating the law of cosines and see how it goes together. Let's now apply it down below. Example 1 says, solve the triangle for the unknown sides. And this is a pretty typical way the homework problems are written out. They didn't give us much. I like these kinds of questions where you have the triangle and you're just ready to go. I make these questions about equally likely as these ones on exams, so we should be prepared to go in either direction. If you see a problem that looks like this one, the very first step is we need to build our diagram. And in our diagram, we have a really tiny acute angle, 17.1 degrees, something that's almost 45 degrees. You don't have to build your triangle perfectly, but the closer and more proportionate you can make it, the easier it is to relate the information. So I'm going to try by beginning with gamma. Here it is, 17.1 degrees. Now for beta, 45 degrees, let's see, maybe, oh, that's not 45 degrees at all. Maybe if I extend out and go about like that, that's about right. Let's make it happen. So this will be beta. I wouldn't worry too much about getting it perfect. Just try to get a diagram that's believable, where you can relate everything together. That's the purpose of it. This is 43.9 degrees going this way. So next we have angle alpha, side length A, which is 32.8 degrees. And that's all we know about this triangle. But we still want to put down more information. If you used uppercase B or beta, we should use lowercase b right here. I'll put a question mark to remind myself that I need to find that side length. And same idea over here. This will be side length C. Whether you use gamma or capital C in this location. So we want to solve for the unknown sides. We have 2 sides right here. But you know what's always a good idea? If you have 2 angles provided, you might as well find the 3rd angle. We did that a bunch of times in section 8.1. It amounts to taking 180 degrees, subtract the 2 interior angles. So let's do it right now to start off. So let's take 180 minus 43.9 minus 17.1, and we get an angle measurement of 119 degrees right where alpha sits. So right here, 119 degrees. Now we can start. Now, let's grab this again. Bring it in as a quick screenshot. This looks like a very unusual example 1, but I assure you this was intentional. Oh, that made that too small. That looks a little bit better. When you really look at this diagram and look at the law of cosines, you cannot actually use the law of cosines on this diagram. Let's explain why. There's 3 different equations that you could use, and they're both start with a side length, a squared, b squared, or c squared. If we're looking here at a squared, we have the angle opposite of it. That's good because you need to have cosine of alpha right here. But what else do you need? You need both of these side lengths around alpha. You needed the B and the C, and both of those are missing. So we can't use that equation. That's eliminated. Let's go to the next one. If you're looking at side length B, you need B squared and you need cosine beta. We definitely have cosine beta. We have all the angles. But you also need A and C. We have A this time, but C is missing. That means you can't use this equation. That one's out. And then the last one we could try is, it's not going to work, but it's all about knowing when law of cosines can't even be used. If you try it this way, you have a C squared. So, well, you need the side length C if you're going to use that equation, and we don't even have that one. So nothing works. That just seems kind of cruel and unusual. But that's what happens with law of cosines when there are two unknown sides. We need to at least know two sides at once in order to apply any of this. So it's not like law of cosines is useless. The issue here is that law of sines is still equally as important as law of cosines. We actually have to start this way. Law of sines. And that's just as well. We're going to review law of sines as we go. Then we could use law of sines again, but just because we have law of cosines, after we use this, we'll use the law of cosines just to see how it goes. Okay, well, any questions, folks, before we start with law of sines this time? Okay, so with law of sines, what would we want to solve for? How about this right here? Let's go for a B. You would put, to start off law of sines, B over sine beta equals, now I need to use a side and an angle where they're both known. So I can't go gamma to side C because C is unknown, but we can go from alpha to side A. Both pieces of information are known there. So let's go A divided by sine alpha. So all I did right here is state the law of sines in the format we're going to use. Next step is just to plug in information. B is the unknown, so it'll stay just the way it is. Below sine beta, we see sine beta itself is 43.9 degrees. Equals A, on the diagram, A is 32.8 inches. It's divided by sine alpha, and we computed that to be 119 degrees in this problem. So that's law of sines now with information filled in. Next step, multiply both sides by sine 43.9 degrees, and we just about have a side length. B is equal to 32.8 sine of 43.9 degrees, and divide by the sine of 119 degrees. We're just about there, folks. Now we have to jam all this into the calculator, see what we get. First, any questions at all to this stage?
Like, do we need to write law of sines in the test or anything?
No, I'd be okay if you didn't write it in. This is
Yeah,
more for the
like,
notes, so if you
yeah.
come back to the notes, you'll know what I was doing at this step.
Can we also say like, can we also start with like C and gamma if we wanted to?
Yes, absolutely.
Okay.
Yeah, this was just my approach. For some reason, I wanted to solve for the side length B, but yeah, you could have done a different side length. Is that what you're asking about?
Yes.
Yeah, awesome. So yeah, you're on the right track if you're solving for C. Any other questions so far? Okay, well, let's now take whichever calculator we're using. I'm going to make an intentional mistake, so stop me if you know what it is. Otherwise, this is what I would put into the calculator. This is automatically wrong, which is kind of concerning. Sorry, say again? Absolutely, that's the mistake right here. Good call. So Michael has identified this mistake immediately. We have to make sure, and you do as well, you're in degree mode. Because in your calculator, it'll save the mode you're in, but if you had to go to radian mode, you might have forgotten when you did that, or if someone borrowed your calculator or anything along those lines, double check you put it in degrees if you're inputting degree measurements. So that was the mistake I was about to make. Thanks for stopping it. Next is just typing this all in as you see it. 32.8 times sine 43.9 which is divide by sine, 119 degrees. And we should all be getting about that measurement. The nearest tenth, I'll put down at 26.0 inches. Does that look right to folks so far in your calculator? Awesome. So we've got one side length down, 26.0 inches. The answer is right here, but I like to put it in the diagram. I just think I have a psychological need to fill in the information here. So I'll also put 26.0 inches. And that also directs us to, we only have one side length to go, side length C. Now, just like Hayes was mentioning, you could just use the law of sines again and find that side length. In fact, that's probably the faster approach. But just because we're practicing law of cosines, I'm going to use the law of cosines below right here to get the side length C.
Do we need to put like everything in like one decimal place or no?
Well, this one's said to round to the nearest tenth, and that's the only reason for it. Sometimes I forget to actually put that into the instructions here. And if I did have something like this, as an exam question or homework question, I would say just use your best judgment. If the information has one decimal place, then that would be a natural choice to round to. I think some of the problems I did forget to put that in, but I do try to be specific on a real exam. Other questions so far? Okay, well, let's hit this with the law of cosines. The formula is down there, but it's so very directed by the pattern that sometimes what you really want to do is practice it this way. Don't look at the formula, just kind of follow your nose. You would take this side length highlighted and go c squared equals. Next, you need to involve these two sides. It'll be a squared plus b squared, and that's already a reminder of that's the format for Pythagorean's theorem. Law of cosines then goes minus 2 times the same variables, a and b, then multiplied by the cosine of, well, if you're looking for the side length c, you have to use the opposite angle, 17.1 degrees. So that to me is a great way to think about law of cosines. It's more about the pattern than trying to memorize whatever the symbols might be that you put on your triangle. So let's put down here, just to orient ourselves on the notes, this is now law of cosines. Now we can start plugging in even more information. Here I put in the angle, but I guess we can leave it like that. C squared is the unknown, so it's just going to be c squared equals a squared, 32.8 to the power 2, plus b squared, that's going to be the value we just found, 26.0 to the power 2. That means we have a little bit of numerical instability right here because it wasn't exactly 26.0, but you know, it's pretty close. It's off by no more than 4,000. So let's go with it. It's going to be minus 2 times 32.8, 26.0, cosine 17.1 degrees. Kind of a nice thing. I did say law of cosines is a little bit longer, but you might question that because even though that's a lot of stuff right here, all of it just goes right in the calculator as one big line. So you might disagree that maybe law of cosines to you is faster on this one. But either way, we're now back to the calculator. This one's not as bad to input. It's just going to be down the line, 32.8 power 2 plus 26.0 to the power of 2. If this really was a 90-degree angle, that would be our answer, but it's not. So we have to go minus 2 times these measurements, 32.8 times 26.0. Finally, we're down to the cosine part of law of cosines at 17.1 degrees. So we get this figure, 121.6394. Doesn't even seem right when you look at that, but keep in mind, we didn't solve for c, we solved for the square of c. Oh, sorry, didn't mean to put that there. So don't be too off-put if you get a really big number that doesn't even seem to fit your diagram. That's typical, we have to square root it. Might be some mistakes somewhere in here. Maybe double check you're in the actual degree mode. That could potentially have done it. Ah, gotcha. For the work down on the paper, I'll put down 121.63. For answer C is going to be the square root of that value. And so we're about to find it. Let's take a look in Desmos. This would be square root of the prior answer, 121.63. One thing I like about Desmos is, as you type in these digits right here, you can see how the numerical output stabilizes. So if I put in another digit, 3, it's, it changed in the thousandths place. So that tells me we already have a pretty accurate answer. Put in a 9 and not much change if I'm rounding to 1 decimal place. I'll call this just 11.0. Sorry, say again? You got exact numbers on that one?
Yeah.
Awesome. Well, other questions, folks, with this so far?
Square root on here?
Oh, good question. Let me pull up my calculator here. And let's see. Yeah, so hit the second button, upper right corner. The power 2 button to the left of your 7 calls the square root. And I bet it types in kind of like this with a parenthesis. Does that look about right?
Yeah.
Yeah, then just feed it to 121.63. Close the parentheses and you should be getting about 11.0. So those 2 keys there will call that square root.
Perfect.
Yep, absolutely. Other questions at the moment, folks, with getting that 11.0 inches?
How does it write log to C?
Just the C here or the angle C?
What side?
Yeah, you would just square root both sides to get your C there. And that's what we eventually did right here anyway, so we got to the same kind of idea. Any other questions so far, folks, with this one? Okay, cool. That's law of cosines in action. And again, the big takeaway in this problem is law of cosines or law of sines, the use of them is always highly dependent on just what information is in your triangle. So when you do these as exam questions, they'll look just like this, and you might use law of sines, you might use law of cosines. It just depends on what this is that's provided. But let's now take a look at the next example. These are kind of nice when the diagram is already filled in. There's a couple of these on the homework assignments. Awesome. How does it go? Is it big or?
That looks like some Greeks in arc. This square. All over.
That sounds about right. What's going on in that formula is they took any one of these 3 right here and just solve for cosine A. So you could subtract B squared, subtract C squared, divide by negative 2BC, take cosine inverse of both sides, and you can do that as a formula. That's not a bad approach. I think our book didn't produce that formula for one reason or another. I think they're thinking if you put in the information and just go through the motions, you're kind of doing the same kind of thing. Well, I used alpha, beta, gamma, so I wouldn't be familiar with that one. Sounds like a pretty wild symbol on that one. Does it look like this? It sounds like a gamma, but I can't be too sure. But now for this triangle, it says solve the triangle. That means you need to know all the side lengths. We do know all the side lengths, so that's done. But you also need to know all of the interior angles of this triangle. So solving a triangle is amounting to, what is that measurement, and that measurement. We need to find all 3. That means we might use 3 different methods to do this. The first method cannot be law of sines. Law of sines fails spectacularly. This is what you might try to do, and I'll delete this in a moment. If you try to use law of sines, you'd go sine A, divide by 15, its opposite side, equals, and take your pick, B or C, maybe it's sine B, divide by its opposite side, 25, but I can't solve this equation. This is one equation and two unknowns, A and B. We just don't have enough information. So law of sines fails to start on this one. Let's make that a statement. We cannot start, oh, gotcha, with the law of sines. So in the example one, we couldn't even use the first formula of the notes, law of cosines. And now example two, this is a case where you cannot use law of sines. We must start off with law of cosines. So if we're going for law of cosines, we just need to pick a side. Let's go for angle C. You might have picked B or A, it's all up to you. I'll go with this one for no apparent reason, just like angle C. Law of cosines says then you're dealing with these two sides. These are like the most extreme sides of the equation. So C is on the very far left, C squared. And the cosine of this angle C is on the very far right. And that means we never used B or A, but it does come into play like this. C squared is now equal to A squared plus B squared minus 2 times A times B. And let me move that a little bit closer, times cosine of C. So this is the start of law of cosines. Notice when you use law of cosines, you're really using up a lot of stuff here. A, B, and C all get into play. And the next step, all we're going to do is just plug in information. C squared is going to be 28 meters squared. A squared is going to be the 15 meters squared. B squared is the 25 meters squared. And once you get this far into your equation, you're just reusing the 15 and the 25. It goes minus 2 times 15 times 25 times cosine of the unknown, C. So that's our objective to get to, solving that equation. That means we're going to section 6.3, solving a trigonometric equation, but we'll do it by using an inverse function. That's why it's more of a 6.3 kind of problem. Like Michael mentioned, there's also a formula that just solves this whole equation for C. That's not a bad way to go. But if you're memorizing law of cosines, then this would probably be your first formula to memorize. I think a lot of people would end up doing it this way. But from here on out, there's some extra computation if you went in this direction. Let's get our calculator out and start just computing these things. Pretty much, yeah. Are you saying instead of C, you have like A right here? Oh, I'd have to take a look at that later on. I'm not too sure. You probably would be okay because it should be a symmetric equation, swapping a letter. But I'd have to take a look at it later to be sure. But now for this equation, we have to square 28. If you did want to take a shortcut to this, you would realize you are subtracting 15 squared, you are subtracting 25 squared, but I'll just write in as we see it. 784 is going to come in on the left. It'll be equal to, back to the calculator. Let me see if I can make this a little smaller. There we go. So I'm going to do 15 squared and plus 25 squared. I didn't mean to hit that. Oh no. There we go. Let's hide that thing. 15 squared plus 25 squared. At that portion, we get 850. So I'll just drop that right here. Then there's a minus and more computation. I'm just going to multiply these things together. That's 2 by 15 for 30, but then a 25. I'm just going to throw the calculator after all. 2 times 15 times 25. Here we have 750. It's really negative, but I put the negative down here already. So negative 750 cosine of angle C. So I didn't do much. I just squared everything out, combined some like terms to get to this stage. Next step is to take 784, subtract 850 from it. That calculator is not going to help me, so let me try it over here. 784 minus 850 takes us to negative 66 on the left-hand side, right over here. Nearly there, folks. Next step in the calculator is just to take your negative 66, divide by negative 750, and we get, looks like an exact figure, 0.088. Equals cosine C. And now this is what makes it a section 6.3 problem. The very next thing you do on this line is take cosine inverse of both sides. So the left-hand side is going to be cosine inverse, 0.088. Right-hand side is going to be cosine inverse of cosine of C, but we have a cancellation always with a function and its inverse. The angle C here is now liberated, and we get C equals cosine inverse of 0.088, provided it didn't make any mistakes in there. Does that look right to folks so far? Over here? That's a good question. Let's see. I think we're going to be okay because a domain error right here would imply that this figure was instead like a 1.088. So that's what would cause a domain error in that kind of situation. So it looks like we're okay in this case because this was in the right range for the inverse function. Other
why
questions
did
at the moment?
why did you
Yeah.
do it double? Can't we just do like cosine inverse of 0.008 and then we get the answer?
That's what we're
Oh,
doing right here. Yeah, absolutely.
I don't know. The middle step was like confusing.
I hear you. Yeah, that middle step is important because that's pretty much the big punchline of section 6.3 on inverse functions. And it does come into a lot of different cases. Like, for example, that's about what's going on right here. If you see sine inverse with sine of pi over 3, we need to know that that's a true cancellation, and you just got pi over 3 back. So yeah, I agree. It's kind of a weird, strange step, but it's important for pattern recognition because that kind of pattern happens all over the place in algebra. If you did skip it, it's okay. It's really more here for the notes. Other questions at the moment?
Thank you.
I think Desmos actually gave me an exact figure, but I'm not entirely sure. Did anyone get more decimal places on that one?
I didn't use my calculator to do it, but I was just curious.
Yeah, I think we got, but I've got a TI-30XA over here. Let me see what this does. 66 divide by 750. Yeah, this one is exact figure at 0.088. Just a weird accident. I would have expected more decimal places too on these things.
Well, let's just assume that there's 50 decimal places.
Mhm.
Where would you go with that?
So 50 places to the right here.
Yeah. There's 0.088142388.
Oh, gotcha. I would probably, if it's an angle like this, I'd probably be keeping about 6 decimal places altogether. Because when you apply the cosine inverse function, it's very sensitive to having round off errors. So yeah, I'd probably be around 5 or 6 decimal places to be sure. These are really good questions so far. Any others at the moment? Gotcha. Yeah, yeah. It just keeps that same precision either way. That's kind of neat. That's a good way to tell you that it was a pretty likely exact figure. But now that we got all there, here's the fun part. In your calculator, it's going to look about like this. We did this last class, so I feel like this is a good do-over right here. And let me actually show the buttons as well. We're trying to learn the calculator at the same time. I think that's important. If you want to use cosine inverse, you have to start by hitting the second key and then hit the cosine key right after. You should see, I think it prints cosine inverse like that. to start off. When you hit second cosine, let me know if it looks different. Next, give it the 0.088. And you should be getting the value I'm about to produce right here. I think on Desmos, I need to go arc cosine. I'm not totally sure, but it seems safer. 0.088. And I'm getting an angle measurement of almost 90 degrees. 84.95 degrees, in other words. Awesome. Looks like that's working out so far for folks. So 84.95 degrees. Let's put it down here. That's a moment to celebrate because there's 3 angles we're finding. We're 1/3 of the way done. Wow, more to go though. Let's fill in here. We've found a part of the answer. 84.95 degrees. You don't have to do that. That's more for me. Let's box this out because we're going to have algebra in lots of different spots. Now we need to pick a different angle and solve for that one. It's all the same, so it's up to you if you want to solve for A or B. We did C, so how about B next? No particular reason, just seems like the next one to try. I need to scroll a ways down, so I'm just going to take a screenshot of what we've got so far. Let's plug it down here. And now, if we're going for the side length B, the same exact approach that we took will work. But you might have noticed, law of cosines, if you're solving for an angle, does feel like it involves a lot of algebra. Because you're not just taking this stuff and cranking it all out. You're really solving something. So law of cosines is a bit of a bother, and it kind of is. Just use the law of sines. It's way, way faster. Now that we have one angle, law of sines can now be used. So let's change gears and use this approach, law of sines. So now for law of sines, I'll write down the formula because again, we only use it for the second time today. If I want the angle B, I would place that into the numerator. Oh, and I made a mistake. Let me try again. This is the law of sines. So if you're talking about the angle B, you have to take sine of that angle B, then place it in the numerator. Divide it by the side length B, and this will be equal to, now we have to use angle C because that's the one we know information on. Sine C, divide by lowercase c. I'm running out of vertical space, so we'll follow the arrow and fill in the information. B right here is unknown, so it's still just sine B. The denominator is 25 meters for lowercase b. Back over here, we do know that angle C, 84.95 degrees. And it's divided by side length C, which we found to be what we defined it, but it's right there, 28 meters. That was provided. Next thing we do is we take 25, multiply it both sides. So sine B is now equal to 25 sine 84.95 degrees divided by 28. Just about there, but we have to plug all of this into the calculator. So let's make that our next step. Any questions so far with the law of sines being applied? Okay, we're nearly there. I have 25 sine 84.95 divided by 28, and it comes out at that angle measurement. That is a comfort because if this was below -1 or above +1, no solutions. This would have been an impossible triangle, or we made an algebraic mistake somewhere. So I'll write down sine B, and I've already forgot the number. Let me double check. Equaled 0.8893. And now we're about to do the same step we did over here by the red dot. We need to apply sine inverse to both sides of the equation, which causes a cancellation right here. But you know, we showed it right here, like Hayes was mentioning. That is an interesting kind of confusing step. Just to show this is correct as well, you're okay to write B equals sine inverse 0.8893, because I mean, that is the punchline right there. You apply sine inverse to both sides. This is more of a connection or a pattern checking thing that is sometimes helpful, but you don't have to write it down each and every time. So if you go this route, let me see if I can get more space. No, I don't have more space to get. I'll just put b equals on the right here. And now we're doing another inverse function. So this time you have to hit second key, the sign button right here. Let me know if you're getting a different value. Up here, I'll go arc sine, start feeding it the digits, 0.88. You notice already at 0.8, giving it one extra decimal place is huge. It went up almost like 10 degrees. Another decimal place, what did it do? It changed by more than 1 degree, it looks like, so that was huge as well. With a 3, now it's changing in the hundredths position, so 4 digits is already important. With a 9, it changed again in the hundredths place, so 5 digits is important. It's all because of the inverse function. These are highly sensitive to change. So 0.88939, at that stage we're stabilizing, so we can call this 62.80 degrees if we're rounding to 2 decimal places. Oh, awesome, so that did work out.
I have a question. So like, can we just go ahead and put like the exact number to it? Because like, we don't know how the decimal place is gonna be. Like as in,
Put the entire number in.
25 sine and like 84.9, and then we just like sine inverse the whole thing. Can we do that?
Yes, absolutely. You'd
Okay.
get the most accurate answer possible.
Okay, thank you.
Yep, absolutely. Thanks for mentioning that. Yeah, when you're trying to calculate, but you want a very numerically stable answer, you would absolutely take that same approach. So for trigonometry, I'm not too worried about that, but in engineering, physics, chemistry, that kind of stuff, yeah, you need to be really careful with numerical precision. So that would be the best approach. But let's put in 62.80 degrees. I'll box this one because we have the second part of the answer. And let's go back up to the original diagram. That one down below is just a duplicate. Not sure if I can really fill that in a nice way, but let's just say with an arrow, 62.80 degrees. One more angle to go. If you can get angle A, the problem is done. Now we could use law of sines, we could use law of cosines. If I wouldn't do any of that, what would you say is the better approach? Good call. Once you have 2 angles, it's always this approach. Highly, highly recommended. Just take 180 degrees. Oh, there's a button there I don't want to press. Still can't find that. F12. Oh, yeah, I was hitting the backspace button, so that makes sense. 180 degrees minus prior answers, 62.80 minus 84.95, gives us 32.25 degrees. So we can now say A equals 32.25 degrees. So there's our 3 answers. We found all the interior angles. And this problem is now finally finished. Kind of a lot of work when you're finding unknown angles, but it was all because I used the law of cosine in its original format, which means now you're doing algebra. You could solve this for cosine C, but now you have another formula to memorize potentially. But we did it, folks. That's the law of cosine so far. We didn't finish the notes. I have a cool formula, Heron's formula for areas. We ought to do at least one application for this thing. So when we return after the exam next Tuesday, or a week away from today on Thursday, we'll come back to finish out these notes here. But any last questions, comments, or observations, folks, on dealing with the law of cosine so far? Okay, I'd say the biggest takeaway after section 8.182 is keep in mind law of cosines, law of sines, they're both equally important. And sometimes you're forced to use one and not the other. It all depends on your triangle. And always remember, that's an awesome formula. The sum of the interior angles of a triangle is 180 degrees. So oftentimes, you don't even need to use law of sines or cosines. Always pick the simplest method is my advice. Well, that's all I have for folks. Have a great night, and I'll see you all next Tuesday.
Oh, one question. We're not meeting
Yeah.
next Tuesday, right? The online people.
That's a good point. Everyone who's in the in-person section will meet on Tuesday. But for folks taking the exam at the Pocatello Testing Center and otherwise, we will not meet. We won't have an actual class.
Thank you.
Yep, you betcha. Sorry, say again? Probably, but I would have to really look into that to be sure. These are the only two that I'm really familiar with, but I bet you there's a bunch of laws related to triangles. There's actually a fantastic amount of math you can do once you start really studying triangles. We mentioned the sum of the interior angles of the triangle is 180 degrees, which begets the question, what are the exterior angles of the triangle? There's a lot of weird stuff you can do.
360.
Yeah, along those lines, absolutely. So yeah, there's just a lot of stuff happening on triangles. It's kind of impressive. Thanks, folks.